So far, we saw that the degree of a continuous map between two compact-oriented manifolds without boundary of the same dimension is a homotopy invariant. Today, we will see Hopf's theorem that says that when we consider maps from a compact-oriented manifold without boundary to the sphere of the same dimension, then two maps are homotopic if and only if the degrees coincide, so that the degree is a complete homotopy invariant. In order to know whether or not two maps are homotopic, we just need to compute the degree, and that's a very cool result. And so we will study this result today. So in order to prove Hopf's theorem, let us consider this technical lemma that is going to be very useful in the proof. Let K be a neat arc of manifold with boundary W, whose dimension is n+1, and suppose that there exists this infinity map F from B to N, where B is a neighborhood of the 2 points in the ends of the neat arc in the boundary of W, such that these 2 points are the unique points whose image is Y, and moreover Y is a regular value. We're going to consider that N is oriented and the boundary is empty. Furthermore, assume that the degrees of F at the ends of K at these 2 points are opposite. Then there exists a map G from U to N such that the following conditions hold. The first one is that U is an open neighborhood of K in W. The second one is that G and F coincide in the intersection of their domains of definition. And the third one is that Y is a regular value of G and the preimage of Y is indeed K. So we are in a situation in which this is W, this is the boundary. We have here a neat arc, and what we are doing is indeed extending the function to a neighborhood of the neat arc, okay, such that Y is still a regular value, and moreover, the preimage of Y is exactly equal to K, okay? That's what we're trying to do and what we are going to prove, okay? So K, okay, our neat arc has indeed a tubular neighborhood, okay? Okay, there exists a tubular neighborhood of K, which is going to be an embedding from the total space of a vector bundle over a K to a neighborhood of K, here is of K, to a neighborhood of K in W, okay? But any vector bundle over K is trivial because K is diffeomorphic to an interval. So our tubular neighborhood satisfies that it's a map from K times, in our case, Rn. It's an embedding from K times Rn to some, I don't know, U, where U is an open neighborhood of K in W. Moreover, by the properties that a tubular neighborhood has for a neat submanifold, if we call, for instance, this point here A and this point here B, what's going to happen is that the image of A times Rn is going to be a neighborhood of A in the boundary of W. Okay, if we consider here the retraction, okay, given by the tubular neighborhood. Here we have TA, the fiber of A, and here we have TB. And the image of A times Rn is going to be TA, right? And the image of B times Rn is going to be TB, okay? But what we can consider now is the composition of such a map, okay? Here we have phi, and here we can consider f, and f goes to n. And the same thing, we can do it for B times Rn. Moreover, we can assume, since the theorem has local nature in the neighborhood of n, that ny is just Rn0, okay? That doesn't change anything. The interesting part of this construction is that these two f's have opposite degrees. But we already know that these maps over here have also opposite degrees. The reason is that when we are traveling along the path K, at one of the points we have to get in, and at other of the points we have to get out. And that actually makes these maps are indeed of different degree, right? So what we get in this way is that the composition of phi and f, which can be considered as a composition from Rn to Rn, these two compositions actually have the same degree at 0. And that's going to be important, okay? So what we want now is psi, which is going to be a map from K times B to actually N, so Rn, such that when we consider phi minus 1 composed with psi, which could be defined actually in a neighborhood of K, right? It satisfies all the properties that we want. That's our goal. In particular, it has to be equal to f in TA and TB, at least in the neighborhood of A and B in TA and TB respectively. Very good, but that implies we have in this way that psi is this composition. And the same thing happens when we consider here B. Okay, but these two maps, phi composed with f, are both at 0. They have both the same sign. The Jacobian determinant has the same sign at 0 for these two maps. Okay, because the degree at 0 for these two maps is the same. In this situation, we can identify K with the closed interval 0, 1, and then we are going to consider a homotopy, an isotopy indeed, defined in some neighborhood P of 0 in Rn to Rn. An isotopy from actually the value of this map, where psi 0 is going to be this composition in A times B, and psi 1 is going to be also this composition in B times B, okay? And as I said, we are going to suppose that psi is an isotopy. This isotopy, of course, is going to provide a continuous map from K times V to Rn. Okay, and this isotopy exists because of this theorem. If we have two embeddings, two local diffeomorphisms, if you want, from Rn0 to Rn0, and the determinant of the Jacobian matrices at 0 for these two local diffeomorphisms is the same, then the sign of the determinant is the same, that's what I mean. Then what we get is that these two maps are isotopic. There is a path from the first to the second consisting just of local diffeomorphisms. Okay. In these conditions, what we get is that it is clear that we were considering the map, this map over here. Okay, and we want to know what's the preimage of 0, but that's going to be the image by phi of the preimage of 0 by psi, which is just k times 0, and this is just equal to k. So the preimage of the regular value is exactly k. And by construction, because of these psi t's are embeddings for all t, what we get is that actually 0 is a regular value of the composition. And so we get a result. The following theorem is a key result to prove Hopf's theorem, and indeed it is more general than Hopf's theorem. Okay, let W be a compact-oriented manifold with boundary of dimension n+1, and consider a continuous map from the boundary of W to the sphere Sn. These two manifolds, the boundary of W and Sn, have the same dimension. Then F extends to a continuous map from W to the sphere, if and only if the degree of F is 0. Okay, the first thing that we are going to consider is a tool that it is useful to simplify the setting. So let us consider F that it is homotopic to F prime, okay? And we claim that F extends to W continuously, of course, if and only if F prime extends to W. So if we can extend some map that is homotopic to F, then we can extend F, okay? Let's give the idea of this claim. Okay, suppose that F extends to W, and so capital F is going to be the extension of small f to the whole W. What we can always do is extending f prime to a neighborhood of the boundary of W. Okay, this is always possible because of the existence of colors. A neighborhood of the boundary of W is just diffeomorphic to the product of the boundary and an interval. Okay, so as a consequence, there exists f prime that it is an extension of f prime to a neighborhood of the boundary of W, right? And we know that f and f prime are homotopic, but it is not difficult to show that there exists a homotopy H defined in some, let's say, U times 0, 1 to Sn, okay, a homotopy from F to F prime, okay, so from capital F to capital F prime. So H of x0 is capital Fx, h of x1 is capital F prime x, okay? And U is, again, a neighborhood, an open neighborhood of the boundary of W. This is possible, okay? It's not very difficult. It happens in the boundary of W, and this happens because F is homotopic F to F prime. Then we can extend a little bit, right? Now, what we have is that the homotopy extension theorem implies that there exists a map J from W times 0, 1 to N, okay, so to the sphere, such that the value at 0 is capital F, the extension of small f, and then we have that this j of xt is equal to h of xt for every t in 0, 1, and some open neighborhood of the boundary of W that can be slightly smaller than U, okay? For all x in this U prime, which is in particular a neighborhood of the boundary of W. In particular, what we get is that when x belongs to the boundary of W and t is equal to 1, then j of x1 is equal to h of x1, okay? But this map over here is capital F prime of x, which is a small f prime of x. So what we get in this way is that the map from the boundary of W to Sn that sends x to capital J x1 is indeed an extension of f prime. Sorry, here it should be W, okay? It's an extension of f prime. And so we got what we wanted. If f extends, f prime extends, and of course, repeating the argument, if f prime extends, then f extends. It's completely symmetric. So extension for all maps in the same homotopy class is an equivalent property, okay? So we have f, suppose that we have a continuous map from the boundary of W to the sphere that extends to W. Okay, in that case, we can consider f hat, which is a C-infinity map because of the density of C-infinity maps, that is homotopic to F. And by the previous result, extends to W. Okay, let us consider that extension. F hat is going to be the extension of small f hat to the whole W, okay, where capital F hat of x is equal to small f hat of x for every x in the boundary of W, okay? Now we can use the usual tricks to obtain another extension of f hat that is infinity, okay? That's not very difficult. So we can modify a little bit. f hat so that f hat is C infinity. And when we get to this point, then now we can use that small f hat, okay, is a map, it's a C infinity map from the boundary of W to Sn that extends to a C infinity map of the whole W. But this setting implies that the degree of small f hat is equal to 0. Okay, we proved already this result. And since f hat, small f hat, and small f are indeed homotopic, then the degrees are the same. So this implies in particular that the degree of f is equal to 0. So any map that extends, even continuously, has degree 0. Now let us consider the other half of the theorem. So let us suppose that the degree of f is equal to 0, and we want to extend it. Our f a priori is a continuous map from the boundary of W to Sn, but we can assume that it is C infinity by considering a homotopic C infinity map, because that map is going to have also degree 0, and if we can extend the second map, then we can extend the first. So without lack of generality, we can suppose that f is a C infinity map, right? And now, what happens in this situation is that we can consider y a regular value of this map, right? And since the degree is 0, what we have is that the number of points that there is in the parameter y is even, and half of them are positive, and the other half is of negative type, right? So we can consider those points in the parameter y, something like this, and half of them are going to be positive, okay, and half of them are going to be negative. And what we want now is connecting every positive point with a negative point by a neat arc, something like this, for instance. I don't know if it's correct. Maybe something like this. Okay. But we could actually consider something like this, and then something like this, and then something like this, and then something like this. Okay. The issue is that in order to apply the lemma, we need to consider neat arcs, that these arcs are not allowed to intersect. We want to work in the neighborhood of neat arcs. So if possible, we want these neat arcs to be disjoint. This is simple if the dimension of W is greater or equal than 3. So when n is greater or equal than 2. Because in this case, these neat arcs are indeed the images of a finite union of intervals, and we can use the Whitney embedding theorem, the Whitney approximation theorem. And so we can, by the Whitney approximation theorem, suppose that by deforming a little bit these arcs, we get an embedding. In particular, this map that we consider is injective, and that implies that the neat arcs do not intersect. So we can suppose that the neat arcs do not intersect by the Whitney approximation theorem. Okay. What happens when n is equal to 2? We cannot do this because we can apply the Whitney approximation theorem because the dimension of W, which is greater or equal than 3, is greater or equal than twice the dimension of k plus 1. In other words, 2 plus 1, 3. But we cannot use this with 2. If we deform a little bit this arc, in this arc, they're still going to intersect because this point is a transversal intersection and these ones are stable by small perturbations. So we have to do something else in order to make these neat arcs indeed disjoint. And what we do is considering this picture, okay? What we have in here is an intersection between two neat arcs. Here we go from positive to negative, and here from positive to negative. And what we can do is actually, when we travel on this path and we get here, close to the intersection point, we can change the path and follow the path, the second path, in the direction of the negative point. And when we follow this path, second path, from the positive to the negative point, we can actually change the path and go in the direction of the negative point for the first path. In this way, we obtain two other paths, and there is one less intersection point. And by repeating this process a finite number of times, we get to a situation in which all the neat arcs are disjoint. For instance, here, it is very simple, okay? If we consider these two paths, it's simple to somehow remove that intersection, because we can consider something like this and then something like this. And we have one fewer intersection at least, okay? So we have here our domain W and its boundary, and we consider the points in the preimage of Y, and we know that we can connect positive and negative points by disjoint neat arcs. Now, since the arcs are disjoint, we can apply the lemma. And the lemma is going to provide an extension defined, okay, an extension of a small f defined in the neighborhood of these neat arcs. But the extension is interesting because it only takes the value y for the points in the neat arcs, okay? Very good. So what we have now is that if we call this, the union of these open sets over here, U, so U is going to be an open neighborhood of the neat arcs, okay, we want, we have that f, small f, has an extension, capital F, defined in the union of the boundary of W and the closure of U. Okay, by considering U as small enough, neighborhood of the neat arcs, this is possible. And we want to extend this capital F to the rest of the points. So we want to extend capital F to W minus U, okay? That's our goal. To extend F to W minus U. And we know that it is already defined in the following set. F is defined in the boundary of U, the frontier of U, union the boundary of W minus U that we can call this set gamma. So it's well defined in this part over here, and this part over here, and this part over here, and this part over here. Okay, and we want to extend it. But we have an advantage, and it's that when we consider F restricted to gamma, okay, this map does not contain Y in its image, because the point Y, okay, the preimage of Y by this map is the union of the neat arcs, okay? And gamma does not contain points in the neat arcs. So by identifying this complement of Y with Rn, we have that we can interpret the restriction of capital F to gamma as a map from gamma to Rn, so as n functions. Okay, and now we can use Titus' extension theorem. Titus' extension theorem says that if we have normal space and a continuous function defined in a closed set, then it extends to the whole space. But every metric space is a normal space, so we can apply it here. And that implies in particular that there exists an extension that we are going to call F, capital F gamma, of the restriction of F to gamma to W minus U. Indeed, it's going to be this extension is going to have images in this copy of Rn that is diffeomorphic to the complement of Y. So the images are in Sn minus Y. And by pasting the two extensions that we got for F in the closure of U and in the complement of U, they are equally in the intersection of the closures, they are equal in the intersection of the closures of those sets. We get that capital F is a continuous extension of a small f to W. And that's exactly what we want to prove. There is an analogous result for the non-orientable case. Indeed, if W is a compact non-orientable connected manifold with boundary of dimension n plus 1 greater or equal than 2, of course, that's the reason that because we consider greater or equal than 2 because all manifolds in dimension 1 are orientable. Suppose that we consider here a continuous map defined in the boundary of W and with values in the n-dimensional sphere, then F extends to a map defined in W and with values in the sphere if and only if the degree of F modulo 2 is equal to 0. The proof of this result is analogous to the theorem that we already proved, and we are going to skip the details. If you want to read the proof, you can find it, for instance, in Hirsch's book, okay? Now, finally, we can provide the statement and the proof of Hopf's theorem. So let M be a compact connected M manifold, okay, with n greater or equal than 1, and let us consider two continuous maps from M to the n-dimensional sphere. Consider the case where M is orientable, and of course, the boundary of M is empty. M is a manifold without boundary. Then we have that F is homotopic to G if and only if the degree of these two maps is the same. And indeed, for every integer number, we have a map whose degree is exactly that number. We have results also for two other cases. The case where the manifold has no boundary but is non-orientable, and the case where the manifold has a boundary. In the case, in the non-orientable boundaryless case, then F is homotopic to G if and only if the degrees are the same but the degrees modulo 2, okay? And there are maps of every degree in the field of integers modulo 2. If the boundary is non-empty, then we have that F is always homotopic to G. So we are going to prove the first theorem. Indeed, it is almost already proved. The other two, you can check the proofs in the book, and the arguments are of similar type. Okay? So first of all, we have that if F is homotopic to G, then the degrees are the same. Okay? We already know that the degree is a homotopy invariant, so no problem here. And now suppose that the degrees are the same. Right, but what we can consider now is a map H defined in M times 0, 1 to the sphere, and that sends every point of the form x0 in its image by F and x1 to G of X, okay? We are going to do this, and of course, the manifold W that we have to consider is M times the closed interval 0, 1. Okay, the degree of H restricted to the boundary of that manifold, okay, it's the following. Since the orientation in the boundary is opposite in M0 and M times 1, in M times 0 and M times 1, what we get is that this degree is indeed the degree of the restriction of H to M times 0, which is the degree of F, minus the degree of the restriction of H to M times 1, because in M times 1 we have the opposite orientation. So degree of F minus degree of G, and this is equal to 0. But now we can use the theorem, the auxiliary result that we said it was going to imply Hopf's theorem, to prove that H has an extension to the whole manifold, to W, which is M times the closed interval 0, 1. And that extension is the homotopy between F and G. So in this way, we have that F is homotopic to G. What remains to be proved is that there is a map for every integer number. So let's fix M, a natural number, okay? And let us consider a few points, x1, x2, xm, different points, of course, in our manifold M. Now consider oriented local charts. Okay, this is going to be a local chart, an oriented local chart. And we're going to require indeed that the target space, that the image of the local chart is the whole Rn, okay. And what else? That xi is a point of ui, so ui is an open neighborhood of xi for every I, and that when I and j are different, the intersection of these two guys is empty. We can do that by considering local charts whose domain of definition is a small neighborhood of xi. Okay. What we're going to consider now is the stereographic projection from actually the North Pole. Okay, this is the North Pole. Well, we could actually call it M to Rn. And this stereographic projection preserves orientation. It's a diffeomorphism that preserves orientation. This is orientation preserving. Now we can define a map that we can call, for instance, capital F from M to Sn. Okay, and so if X belongs to UI, the definition of capital F is going to be, okay, the preimage, the inverse of pi composed with phi I. This is actually well defined, okay? And if X does not belong to the union of the UIs, we define Fx as being just equal to the North Pole. It is easy to check out that this map is indeed continuous. And if we consider a point Q in the sphere, which is different than the North Pole, what we have is that the preimage of Q has exactly n points. Moreover, these two maps preserve orientation, so the degree at these points is exactly equal to 1. Okay, these maps indeed in UI are diffeomorphisms from UI to its image. And they are orientation preserving diffeomorphisms. So the degree in all these points is equal to 1. So the degree of the map built in this way is equal to n. It is very easy to obtain degree minus n. What you have to do is simply considering local charts in here that are orientation reversing. And so this map over here is orientation reversing. And for any of the endpoints in the preimage, the degree is minus 1. So the degree of our map is minus n. And degree 0 is even simpler to obtain. A constant map has always degree 0. So we can obtain any possible degree, any possible integer degree. And so what we get, because of Hopf theorem, is that there are as many classes, as many homotopic classes as integer numbers. There is a bijection between the set of classes modulo homotopy and the integer numbers. In this lecture, we proved a very cool theorem that when we consider continuous maps from a compact oriented manifold without boundary of dimension n to a sphere of dimension n, then the unique homotopy invariant is the degree. In other words, two maps are homotopic if and only if the degrees are the same. In our next lecture, we are going to introduce a new concept that is related to the degree of a map. It is the intersection number. We are going to define the intersection number of compact oriented submanifolds of an ambient space of complementary dimension. And indeed, we need such a concept, such a construction, in order to present later on two very important theorems: the Poincare-Hopf theorem for vector fields and the Lepchat fixed point theorem for self maps. Thank you for your attention.